Good afternoon, everyone. My name is Mark. I'm with a company called Seacom. We are a submarine cable operator between Africa, Europe, and the Asia Pacific. And I'm just going to talk a little bit about what we did with regard to route reflection on VMware and so forth. The use case here looks at Cisco as the tool that we used, but this could apply to any VM-based route reflector that you can deploy in your own network. So we're not endorsing Cisco here at this point. So to start off, we have the usual n-squared problem. This is a typical fully meshed iBGP network, and we normally resolve that with standard route reflection, or unless you're one of those that prefers to use confederations, you would obviously go for a route reflector setup. And in this case, obviously the iBGP client has a BGP session with the route reflector, end of story, and that tends to scale very well. Now, the previous models that also still used today for route reflectors, obviously, is to use a regular router, as you would for a route reflector, would typically be either in path, so this would be your core router because it's right in the middle of your backbone, or would be out of path, which is what we're seeing day to day, especially with the MPLS environments and so forth. Many of you would be familiar with this kind of hardware. I think many of you have used one or more of these as route reflectors at some point or other in your careers. I have to admit I've used an M120 before as a route reflector. Not a terribly good idea, but it does do the job as well. The old JCS Junipers used to be good, but those got wasted also. So what are we seeing now in this space in terms of requirement? We wanted something that could give us a lot more control plane memory. We needed, obviously, smaller devices because co-location space is a premium. Out-of-path topology is obviously great if you use an MPLS backbone or if you want to decouple your core from your routing. One of the big advantages, obviously, with doing this sort of route reflection is you decouple your fib from your rib. And that allows you, of course, to speed up convergence because, as we know, programming the fib is a large part of convergence. And if you can keep that away, you can speed up your BGP table. Using commodity hardware obviously tends to be cheaper than regular routers across the board. Virtualization means that the VM could be portable, the configuration is easy to back up, you can move it also, you can migrate it and so forth. And then obviously innovating through software and not having to rely on needing new hardware to get new code. And then obviously the limitations of slow CPU in routers, low memory and so forth. So this time proper software routers, not the software-based CPU forwarding that we've all been used to. This is now real software. Vendors have been working on this for a while now, and because of the entire SD and NFV debacle, we now have a bunch of VM-based routers that were not primarily built for route reflection, but found themselves in that role anyway, and that makes sense. To use them for that. And obviously vendors picked that up and have developed the technology even further to allow us to have proper route reflection technology in the code. These are some of the ones I'm aware of myself. We use the Cisco CSR1000V. We'll go into that a little bit, but there's a bunch of others, as you can see, from Cisco, NXOSV, XRV, and so forth. Juniper's VRR and VMX, Alcatel-Lucent, now Nokia with the VSR. Brocade's Viata is also quite popular. And implementation will obviously be quite simple. Normal x86 hardware, deployed as a VM image, and those are all the hypervisors that we know could work with the one that we used anyway. So the deployment for Seacom for us was essentially a CSR1000V, which is basically an ASR1000 without the hardware. So it's basically iOS XE. And the deployment for us, again, is out of path. So this is not part of our core. It sits outside of the forwarding path. Just to show you that they actually do exist and actually work, on top of that big bad router there is a little server there, a little HP job. As you can see, that is an actual route reflector running iOS XE as a VM. And that's another POP front and back of the same. So they actually do exist. Kit-wise for the server, we went obviously with HP, but you can go with pretty much anything that has x86 hardware. We wanted something that was scalable, occupied very small footprint, and could keep running for years on end. Main thing to note here is that many of the server vendors obviously say do not max out the memory because then you lose performance. So you either get performance or you get capacity. In fairness, 512 gig of RAM is more than enough. So that box is capable of about 768. So we've got about 90% memory installed in the box. The other thing to note also is the 4-port Ethernet line card, which I'll talk about later. We run VMware SSI 5.5 on that to start, and then obviously Cisco CSR1000V on top. The reason we went with Cisco is generally because at the time, this was 2014, our other vendor, Juniper, didn't have a real solution. VRR, which is now VMX, was still sort of still being tested. There was no real mature code then. And obviously we didn't, we're not a Nokia house or a Brocade house. So, Cisco was the ideal option. They obviously did have XRV as well, but as we've noted, XRV, like Junos, tends to be a bit verbose config-wise. And while the route maps can be a bit unwieldy in iOS and iOS XE, they tend to be reasonably okay to follow. So you can imagine what the config looks like. Reasons for going out of path. Obviously, when you have different vendor equipment for different parts of the network, it becomes easier to have a single system that you can use to standardize your config and your setup. Obviously, BGP, in this case, BGP for IPv4, removing that out of the core means that you have less impact on your core routers. Obviously, less impact on the control plane in the core as well. The core doesn't have to be part of your routing convergence because then there's no BGP running in the core for IPv4 anyway. We'll still run it for IPv6. For day-to-day operations, the NOC can stay away from the core routers, which tends to be a very good thing. Any backbone flaps in the core don't translate into CPU impact on your routing, which is obviously great. You can obviously then run the latest features for routing and not have to worry about how that would affect your core. And obviously that also means you can run slightly older RPs or control planes in your core, and you don't have to upgrade those because you're running that as a route reflector either. The problem, though, obviously with out-of-path route reflectors is that they make the best path selection obviously based on their view of the IGP backbone. So, a route reflector in one POP making a decision for an iBGP client, another POP will have that as a point of view from that area. And you can mitigate this obviously with stuff like add paths or BGP ORR. But in what we've seen so far, I think it's only iOS XR and maybe Junos 15.16 that has this implemented. We haven't yet tested it on CSR1000V. But then also we have quite a number of these route reflectors deployed everywhere, so that tends to work okay. Some details about deployment. For the CSR1000V, this is as of iOS XE 3.17s, and the strange thing Cisco are now calling Denali. I don't know really what that is, but it's some new reincarnation of iOS XE. Supported on all those hypervisors. Obviously, Denali won't run on Citrix yet, nor will it run on Hyper-V, but will also run on AWS. You'd be really brave to put your route reflector in the cloud, but that's an option also. We obviously went with ESXi. At the time in 14, it was the flagship hypervisor for CSR1000V. Obviously, the rest have now come up to scratch now. We're now at 6, but we started off with 5.5 in 14. And the 6 upgrade was just recent as well. We run the units as independent devices. We don't try to do anything fancy with cloud management or any sort of thing. They're essentially an island on their own. This is critical infrastructure, so we're not trying to get too sexy with it. Cisco shipped the CSR1000V in multiple formats. We obviously went with the ISO image, gives you a lot more options for deployment. But then again, the documentation, well, at the time sucked pretty bad. So it took us a little while to get around the setup, and that, I think the documentation is much better now, but at least, you get the chance to customize your deployment a lot more with the ISO image. The bin file is quite nice because that's just a simple regular upgrade, upload, reboot, and then you upgrade it. So that tends to go well. On the network side, like I said, there's a 4-port Intel NIC inside the server. 2 of those ports obviously used facing the core, that's in the public domain. The other port is used internally to manage the ESXi itself, and there's 1 port free. For out-of-band management for the server, we use ILO for that, and that tends to work pretty good also. For the security, obviously, the ILO port management of it is inside a VPN, a private network. And then obviously the 2 core-facing ports and the public domain, as they would normally be. SSI setup is quite straightforward. The only thing I'd recommend is to enable SSH, which is not done by default. That's how you tend to copy CSR 1KV from your device, your laptop, to the server. And obviously IPv6 would be good to have. It's not on by default. The installation of CSR1000V itself, done via vSphere. The vSphere client only supported on Windows today, unfortunately, but they do have a web-based version that can run on any browser. What we found was that when you try to assign physical memory, it's sort of translated to hard drive space. So we had to make enough room on the hard drive as there almost was for memory to make that work. And not utilizing or not allocating all CPU and all memory to the VM also meant it could start. The first time we tried it, it didn't start at all, at 100%, obviously. The vSwitch, which is the default layer 2 bridging in ESXi, needs to be reconfigured. It's by default running in promiscuous mode, so almost every port will be in every other port's life. So we had to create new vSwitches, sort of like VLANs, if you may. Jumbo frames, so ESXi unfortunately only goes up to 9K. So our network is about 9216. So that means obviously you'd have to fix that. And since we use ISIS for the IGP, we'd have to set the CLNS MTU to something below that for the IGP sessions to come up. We turned off power management to increase performance of the VM. And the installation itself can take anywhere from 45 minutes to about 50 minutes, so you could take a useful break. Initial boot requires quite a number of installations, so that would take about 20 minutes, but after that, every other reboot or boot is about 5 minutes. That's good. Licensing is important, as you can imagine, because after 60 days, the server dies. And if you're running critical infrastructure like route reflectors, not licensing your ESXi is pretty bad for business. So. This is, I don't know how clearly you can see that, but that's just the dashboard of the vSphere client and what the VMware ESXi looks like. This is the summary of the server itself. That's the VM. Play, stop, pause, normal things, nothing fancy. That's the vSwitch, as you can see. vSwitch, there's 1 vSwitch for each port, and the 3rd vSwitch is for the VM itself, for the management of the ESXi. Again, if you don't do that, you'll have a large broadcast domain with everything talking to everything, so that's not good. Again, Cisco don't capture this in the setup. That's the VMware ESXi console. It's like a regular console. It's not very fun, but once you have up and running, then SSH is your friend. But it's there for worst case. This is where you tend to assign resources like number of cores, amount of memory, hard drive space, etc., and you can flick that at any point in time. You have to stop the VM, fix that, and then start the VM again. All right. Different iOS XE releases obviously have different hardware requirements. It will determine things like the number of vCPUs that you need, amount of memory you can assign, hard drive space that you can employ. Minimum obviously is 8 gig on ESXi. And you might be used to splitting file systems across different hard drives, but with ESXi and CSA1000V, it all tends to run on one logical hard drive. So you're sort of like a RAID, if you may. And then obviously the minimum EXSI version required to run a specific version of iOS XE or CSA1000V. The licensing itself is also quite important. The more money you pay, the better features you'll get. I think as of iOS XE 3.14s, it can now do up to 16 gig of RAM. We, I think, are licensed for 8. We initially took the premium. If you look at the second last line there, it was initially standard, advanced, and premium. After moving to 3.13s and later, it now becomes IP-based security AX and APPX or some other thing. Anyway, AX is the equivalent of premium, and the license ports over. The premium license obviously gives us, I think, a 500 meg throughput and I think an 8 gig RAM. And also you get all the features, BFD, ISIS, etc., etc. In terms of day-to-day work, it is essentially a router. No surprise there. We utilize BGP selective download. If you remember Joel Yeagley's presentation, I think from 2 days ago about partial fibbing, it's pretty much the same thing. Have control of what you install in the fib. That way, you know, we keep the convergence speed up. So all this runs in control plane. We don't get to program the fib. Upgrades, just a normal bin file, and you're good to go. Just upload, reboot, happy days. ESXi itself is a whole different drama. And between 5.5 and 6 is different vSphere clients, but that also went okay. We're now at ESXi 6. We saw that installing the V6 table, which is about 32K entries for now, is about a second, and about 20 seconds for the V4 one. CPU idle is about 1 to 3%. Remember, this is obviously x86 with 24 cores. It's high capacity, so this is obviously different performance than you'd get from a regular router. We're now looking at about plus minus 300 to 350 routers in terms of iBGP neighbors, majority of them being in the access, because we extend MPLS and IP all the way into the access. And about 80% of these routers exchange the full BGP table. Not an issue at all for a CSA1000V or for this deployment. Again, I spoke about MTU. 9,000 bytes is the max you can get on ESXi. So you need to tune your CLNS accordingly to get your IGP or ISIS or OSPF sessions going. One issue we found many times is obviously the servers are much more sensitive to temperature. So when we've had HVAC failures or power failures that took out the AC, the server tends to go first because it's much more sensitive to heat, unlike the router. So that's not very good. They need lots and lots of cooling. We also came across a huge bug in the ILO in 5.5 that has a patch now, but essentially crashed the machine from time to time for various unknown reasons. But that's now fixed in 6. And obviously all address families are supported, including multicast, VPN v4, VPN v6. No issue there at all. For the future, well, what can I say? Development is ongoing. I think the main thing we'll see here is increase in support for symmetric multiple processing. We'll obviously see much more support for more memory, 64 gig, 128 gig, and whatnot. And obviously, if you have that on your servers, you'll be bright and happy. But in fairness, you're just doing, at 8 gig, we can hold as many as maybe 30 million entries. It's not a real issue. So this can last a long time. The main thing, obviously, is to be concerned about is failure scenarios, moving past on servers, and so forth. But the thing for us, the only thing we've seen fail is temperature-related outages. But beyond that, hard drives have been okay. Fans, CPU, power supplies, and so forth. But, as you know, you hold your fingers. For us, it's a proven technology. We'll continue to invest in it. Not going to be spending any money on dedicated routers for route reflectors. And what we're now focusing now on is testing this kind of thing in OpenStack, but obviously for non-routing scenarios. That's it.
Rüdiger Volk, Deutsche Telekom. Well, okay, nice report. To some extent, I remember 10 years ago, I was talking to vendors and, well, okay, some would have had it very easy to give me the root reflector in run-off-the-shelf box. Didn't happen that back then, and I had much indication from what the vendors were doing that, well, okay, actually taking care of the specific requirements of root reflector applications was not a business case for them. These days, I don't know why they find a business case there. From the operator's point of view, I actually would ask, did you consider doing something on an off-the-shelf box with software that is not bound to the development cycles and the product management decisions of certain vendors?
So you mean like Bird and OpenBGP, something like that?
Like Bird, iBGP, and stuff like that. And kind of for Bird, yeah, I expect the IXP twist of the development environment there does not point me there, but I think the question, is there something else out there, I think is a very interesting one.
I mean, thanks. So we did, and I mean, to be honest, for our Anycast DNS and TACAC servers, we run Huaga and Zebra, and we initially ran ISIS on that, and that sucked, still sucks pretty bad. So we're running, a production environment, for profit. So we tried not to play that kind of game. So yeah, we did think about it. We considered it. We actually also looked at, typical hardware as well in 2014. But for the commercial business we're running, it just didn't make sense. We need to sleep at night.
He's a network engineer. Okay, hey, this is Brad with Rackspace. Thanks for sharing that. I've been looking for someone that's done this in production at large scale, so thank you for that. When you did the migration, you probably had hardware-based route reflectors before. Did you just swap both of them out? Or did you do hardware and your virtual route reflector in parallel for a while? What was the migration like?
Fortunately for us, it was a new deployment. So we had, I feel a bit embarrassed to say this, we had all GSRs somewhere running the backbone, and those were also doubling as route reflectors. So we spent a lot of money building a completely new backbone. Remember, we're submarine cable operators, so IP was a new thing for us. So we spent a lot of money deploying a parallel network, and that's where we threw the route reflectors in. So the migration was interesting, particularly from an IGP standpoint, because we had OSPF trying to bridge two ISIS domains that couldn't talk to one another. That's a presentation for a whole other day. But think VJ Gill and those days. So yeah, the IGP was the biggest issue, moving that across. The routing itself was fine. But yeah, it was an entirely new network, so it was easy to cut over from that perspective.
Matt Petak, Yahoo. Great presentation, Mark. Thank you very much. I'm a little curious. This looks great as sort of the overlay on the side, but you didn't say anything about any challenges you run into whenever you have the client A can talk to route reflector, client B can talk to route reflector, path between A and B is broken. In a virtualized scenario like this, how do you actually ensure that the underlying network layer reachability information is accurate and that your route reflector isn't busy telling two clients, hey, rock on, talk to each other, when they actually have a broken path between them?
So it's a bit easier for us because we, despite the size of the network, we actually do have local route reflectors in every POP. So it's easy, but I understand that that's not the case for everyone, and also some networks are too wide to support that. So that could obviously be an issue, and that could make the case for in-path route reflection. But then also to your point, the optimal route reflection spec that is being developed to support decision based on local and remote clients is one that I know has been implemented in iOS XR and in Juno 16. I haven't yet tested it myself because we're running iOS XE, but we're pushing Cisco to get that code out. But yeah, we're pretty much covered for every POP, so that's why it's not an issue for us.
It's Brad again with Rackspace. Just a real quick question. What was your thought process on landing it with CSR instead of XRV?
So I normally teach some BGP routing workshops, and we started using XRV, or was it Viral, I think, and it felt pretty heavy then. It's a lot better now, so that was one reason. But also, like I said, RPL is much more effective and a little bit stronger than route maps. But like I said, it tends to be quite verbose. So stuff that you can do with route maps in classic iOS XE in 4 or 6 lines would end up easily being double that in RPL, depending on the complexity of your routing policy. So that was another reason that we didn't go for XRV.
This is Vivek here. Any thoughts on the conversions you saw on the route reflection in terms of performance?
Yeah, so like I said, it takes a single BGP route reflector about 1 second for IPv6, about 20 seconds for IPv4, and then that's a good starting point. And then once that radiates through the network, it becomes a lot faster. I haven't really measured empirically the time it takes, but we haven't seen any significant issues in terms of day-to-day convergence, new prefix, new metric, new whatever, or failure-related convergence. Nothing that has given us the reason to actually sit down and measure it. So it's not a concern at all. Not a concern at all. All right. And that's it. Thank you.